Hi, we are EECS 203, Group B44 at the University of Michigan, and our group is consisted of Patrick Hobbs, Peter Jung, Jason Terranova, and Meredith Monticello, and today we will be discussing the Monty Hall problem. So what we want to find with the Monty Hall problem is, if you're on a game show where you are given the choice of 3 doors to pick from, one of these doors has a car behind it, and the other 2 have goats. You want the car. So if you just pick one of the doors, say you pick A, then the host will now open one of these other doors that does not have the car behind it, because the host knows which door has the car. So if he opens, let's say he opens C, then you know now C has a goat, that's a goat. So now what you want to know is, do you want to switch knowing that now this door has a goat behind it?
Alright, so to solve that problem, we're actually going to be considering the 3 doors. C. Alright, so say you picked A. And the host still has B and C. Because originally each of these were 1/3, the probability of you having the car is 1/3, while the host having the car is 2/3. Now, pick A. Say if the host takes one away, the host still has a chance, 2/3 of a chance of having the car, even though he took one of the doors away. Well, you still only have 1/3. But then note that all the 2/3 chance of having the car is now located in B. So in this case, you will want to switch, because the probability of B having the car is now 2/3, while the probability of A having the car is still 1/3. And if you switch, you are actually going to have 2/3, while host only has 1/3. That means you have a higher chance of having the car. Now, what we're going to do is we're actually going to see what happens when there's more doors. So let's say you're playing with 4 doors. And then the host says, pick a door. And there's only 1 car and 3 goats. So let's say you pick A. Now if we draw a chart again, the probability of you having the car is 1/4, while the host having the car is 3/4. Now the host says, I'm going to take it away, and I'm going to tell you that there's no car in B. So now what do? You notice that after you take it away, the 3/4 chance is actually divided between C and D. So then C and D has a chance, the probability of them, of either one of them, or the probability of C having a car is equal to the probability of D having a car, which is this over 2, which is actually just 3/8, which is much higher than 1/4. So let's say you switch. So if you switch, then you get 3/8, and the host gets the other one is 3/8 plus 1/4. So let's say you choose C. So if you choose C, then you have 3/8 chance, and then the host has A and D, which combine to have 5/8 chance. So now let's say the host takes another door. Say, I'm going to tell you right now that it's not in A. Alright, so now what do you know? Note that the probability of D having a car is still 3/8, while the probability of A having a car was still 1/4. So you end up with a situation where you have C and then you have D with the host. In this case, he asks you to switch, and it really doesn't matter which way you do it, and there's really not that much way you could improve your odds. But so the correct way to do this, or the optimal way to do this, would actually be say you start out with Alright, so if you have 4 doors and the host to says pick one, you pick A. So the probability of you having the door again is 1/4. The host having it is still 3/4. And then the host says B is not the right answer. So C and D has a probability of 3/8 again of not having a car, of having a car, or you said 1/4. But note that if you say I don't want to trade this time, the host and the host again will after each round take away another door. Then what do you do? You will notice that the host still has 3/4 chance of having the car, and then you still only have 1/4. But that 3/4 is only reduced to door D. So now the host still have a 3/4 chance, and D has a 3/4 chance, where A still has 1/4 chance. And then since there's only 2 doors, you have to switch, or you are better off switching, because then if you switch, you get D, which is 3/4 chance, and host goes with A, which has 1/4 chance. Now this actually works for every single possible number of doors. So the moral of the story is, if you're in a situation like the Monty Hall problem, you only want to switch the doors when the host has eliminated all but one door on his side, and then you switch that one door with your own door, because the host has all of his probability of having a car on that one door remaining.
Thank you for watching our video. And remember, to find more videos about discrete mathematics, go to knowatom.com. That's KNOATOM.com. Go there right now.